Okay, everyone, hello and welcome to session 9. Uh, in today's session, we are actually uh, studying the structure of the aircraft. So, the structure is like a skeleton or a framework. Inside the building, you have columns, you have floors, you have walls. So aircraft also have a structure with the same function. The function of the columns and the floors and walls is to actually carry the loads or protect the human inside the building, and also it serves as a framework to attach other systems inside the house. For example, electrical systems or the pipings and stuff. So the structure of the aircraft also has the same functions, and these functions are actually illustrated in these three figures in here. So this picture here on the left shows a glider with the lift distribution acting on the wing. So the lift force over the wing is sketched in here, and the structural elements in the wing has to carry the load, the lift load, and also pass this to the center of gravity of the glider to make the equilibrium. The second picture illustrates the protection function to protect the passengers, the crew, and cargo. These are all should be protected against all kinds of hazards, like even if airplane crashes or maybe some less severe damages like the impacts of hailstorms and so on. Also, the structure protects the passengers from the harsh or cold environment. Like when you fly at 11 kilometers altitude, the temperature will be minus 60 degrees Celsius. And the last picture on the right shows the third function, which is the capacity of the aircraft structure to provide attachment points for many other systems. For example, in case of aircraft, it could be the hydraulic and electrical systems, the blankets that are used for the isolation, and etc. If you look at the use of structures during the history of aircraft, uh, you can make the overview as presented in this table. So in the early times, from early of the beginning of 20th century, the aircrafts had the truss structure, and you will probably know about the truss and these kind of things in the static course. Of course, they had the wooden wings, and the structures were made of, um, for example, steel tubes, steel wires, linen, and other textiles. And of course, you had wood in this structure. But in the early 1930s, aluminum was introduced, and it is still in use in many aircrafts today. Although after the introduction of composites, we can say that a new era has begun by the introduction of composites, and you see all those Boeing 787 and Airbus A350s by the introduction of the composites today. On this picture, you see a sub with camel. uh, this aircraft is from the First World War. And if you look at this aircraft, you can see a number of typical features. First, the wings, which are very thin. And due to this small thickness, it's difficult to design a very strong and very stiff structure inside the wing. Uh, Fortunately, this aircraft has two wings, as you see, and it is called a biplane. And both wings will support each other and provide extra strength and stiffness. This is done by the struts and wires that you can see clearly, which connect both wings together. And the fuselage of this aircraft, although it has a small metal plating in front, it's made of a truss structure which is covered by linen. Beside the structural advantage, a biplane had a better maneuverability. But biplanes do not only have advantages, they also have some disadvantages. First, the airflow around wings affect each other, and also two wings result in higher drag force, of course, during the flight. And last but not least, it's increasing the wing area by an extra wing actually does not imply that the lift forces will be doubled. So you remember we had this lift force and the coefficient of lift equation. In there you see this area. So, but doubling this area does not necessarily meaning to doubling the lift force. The two wings of a biplane actually offer just 20% more lift than a monoplane. Therefore, in the end, monoplanes got the upper hand, and you don't see biplanes these days. In later years, for example, in the 1920s and 1930s, the thin wings actually were replaced by thick wings, mainly for aerodynamic reasons. This also gave the opportunity to use the inner space of the wing to create a strong and rigid wing structures. And these structures were made of wood, actually you see as shown in these pictures. And you can see the big spar and all the wing ribs. See the spars and these ribs, and they have many holes, actually you can see in here, to create a lightweight structure. The skin of this structure is fabric or textile or plywood, but it's not meaning to carry the loads. It's only the wing. A very famous aircraft in those days using such a wing was actually Fokker 7. And this aircraft was very successful in Europe and also in United States. And the wing was very thick wooden wing covered by plywood, and the fuselage was a truss structure covered with linen. And the linen had only a protective function, keeping the bad weather and the cold weather outside. So you can perfectly see the inside structure of Fokker 7 wing. This is that structure, and as we said, this wing was entirely made of wood, which could only be made by very skilled carpenters. So this was actually an art those days. As you can see in the table, from the 19th century, 1930s, let's say, until today, the aluminum entered the aircraft industry. And after the Second World War, the jet engine was introduced in civil aviation, which enabled airlines to fly much more longer distances. And these flights were performed at very high altitudes, which requires the cabin to be pressurized. So we have a pressure cabin concept. And after 1970s, let's say the importance of composite structures increased. First as material for secondary structures, but today composites are used as materials for primary structures like wings and also the fuselage, as you see in the Boeing 787 and also Airbus A350. So the transition from aluminum to composites is very comparable to the transition which took place in the 1930s, yeah, as you see in the table. Douglas and Boeing were some of the first companies to make planes entirely made of out of metal. The DC-3, Douglas DC-3 shown in this picture, it took its first flight in 1935 and became really famous. Its earlier versions, the DC-1 and also the DC-2, they were also made of metal, but they weren't as well known as this DC-3. Uh, these planes used aluminum alloy for their structure and outer covering, which was pretty new back then at that time. And they were held together with rivets like those used in bridges and ships, you know. But these rivets stuck out, and they weren't very good for flying smoothly. Later, we had these countersunk rivets, which were introduced, and they resulted in smooth outer surfaces. So the pictures on the left reveal that the aluminum was quite new at that time, and if you examine the surface closely, you'll notice it's not very smooth, and these rivets are placed at very irregular intervals. Sometimes they are really close together, and sometimes um, they are very far apart. And this suggests that the manufacturers struggled to find very skilled designers and craftsmen. And unlike with wooden planes, uh, where carpenters uh, were very abundant, you can find carpenters. The variation in rivet patterns wasn't a big issue since the number of flights was limited, and there were no pressurized cabin yet. And comparing these old pictures to the ones on the right, uh, you'll see a very huge improvement in the quality of metal structures. And the modern aircraft fuselage shown in the right pictures display a much more refined construction, and you can see the skin, the circular beams, um, the circular beam element, which is called the frame, and the also these blue, black or blue, or here these green longitudinal profiles, which are known as uh, stringers, and so on. So this type of a structure is called a shell structure or semi-monocoque structure. These were the skin plays a vital role in carrying the loads and providing protection. We said that in the earlier versions, the skin was not a load carrying part, but in the new ones, the skin is very important. This is a departure from those early days of flight where you saw the linen or textile skins were used. So we have the monocoque structure in here, and also the semi monocoque structure with all those uh, uh, parts like the skin and the formers. So the modern structures, we can actually uh, categorize modern structures into three: the shell structure, monocoque, and semi-monocoque. In the shell structure, you have a very thin load-bearing skin with stiffening elements. In the monocoque, the upper picture, you have only a load-bearing skin, but in the semi-monocoque, you have some supporting elements as well, like these stringers and stuff. Uh, Even though the uh, skin bears a significant amount of weight, not all parts of the structure share the load equally. This is why we classify structural components into uh, primary and secondary structures. So the primary structure handles the main loads, and if any part of it fails, it could lead to a very catastrophic thing. And these key components are referred to as principal structural elements, or PSE, or primary structures, as we said, and they require regular inspections during aircraft operation. On the other hand, you have the secondary structures, which bear smaller loads and serve protective purposes and provide access to compartments. So example of these include the hatches, like this hatch, and fairings. You see the fairings for aerodynamic reasons. You have the fairing when you connect the wing to the fuselage. You should also add a fairing just to smoothly uh, transiently go from the wing structure to the fuselage structure aerodynamically. So elements of the secondary structure are termed non-principal structure, uh, as you see in here. Uh, the fuselage of the aircraft serves as the main body of the aircraft, where the wings, the tail plane, the canards, which you cannot see in here, the vertical fin, and engines also are typically attached to. If it is a single engine, so single engine normally, generally, it will be connected to the fuselage itself, not to the wings. Uh, in some designs, the engines and landing gear also connect directly to the fuselage, and as you see in this picture, in modern civil air transport aircraft, the fuselage resembles uh, as a tube. So it accommodates the flight deck, the passenger cabin, the freight holds, and most of the necessary equipment for operating the aircraft. So for passengers, planes flying above 10,000 feet, the fuselage also acts as a pressure hull, as we said. So this ensures that a cabin altitude of almost 8,000 feet will be maintained during the normal flight operation. So whatever happens, I mean, if aircraft just ascends to some higher altitudes, the cabin will be pressurized to maintain this 8,000 feet pressure. Uh, in this picture, in here you see the structure of a small aircraft, showing the fuselage with the frames. You can see them clearly, and you can see the stringers along with the wing box featuring spars and ribs and stuff. So these components collaborate to carry the loads and safeguard the payload and systems. So when a load is applied at the wing tip, this load, for example, load F, the structure must transfer somehow this load to the virtual center of gravity of the plane to maintain the equilibrium with other forces. And this requires a load path. You can see this load path within the structure. And in this scenario, the load is initially transferred through the rib to the main spar, and then it is being directed to the center of the aircraft from the, utilizing the main spar. So one student might question whether there is a maximum limit to the applied forces or not. So to know this, we can refer to the following diagram, which we call it as a load diagram. This diagram depicts the load factor N. It is denoted by N, and it is actually it is a function of the aircraft velocity. It's in this graph, the load factor is non-dimensionalized, but the velocity is in knots. Uh, the velocity is the same as airspeed also. So this load diagram illustrates what's known as a flight envelope, within uh, which the aircraft should execute all maneuvers. So the boundaries of this envelope are defined by speed and load limits. So the load factor N represents the ratio of lift to weight. The load factor N is lift to weight. So during the steady horizontal flight, like the cruise flight, this ratio is generally 1. The lift is equal to weight, and it is indicated by this horizontal dotted line or dashed line in the diagram, n equal to 1. When the aircraft performs maneuvers such as pulling up or making turns, the lift surpasses the weight, resulting in a ratio greater than 1. And there are constraints on the severity of these maneuvers. They shouldn't exceed certain limits determined by the strength of the structure and its design. For instance, the fighter aircraft typically have much higher limits compared to civil aircraft, and it reflects their robustness in their structural designs.